Okay. Thank you, Professor Ali, for the nice introduction. And a very good afternoon to all present here in the meeting. So I could see the count currently is 68. And I think a few people are still joining. Okay. And most of the people have turned off their cameras. So because this pandemic has given the ease of attending these FDPs or MDPs, or say organizing these things in a hybrid mode where people can learn from different geographical locations, and there's no need of having a physical presence. Okay. So before I begin with the topic for the today's session, that is hypothesis testing, I have a few things to share, and surely we can reconnect if it is required. So firstly, while we are going to study hypothesis testing, the first thing, there are some prerequisite, or say there are requirements before we land up into this topic, hypothesis testing. So the question is, how many of us are familiar with normal distribution? How many of us are familiar with sampling distribution, sampling, and estimation? And then probably we may talk about hypothesis testing. So may I get some responses so that I can have a clear idea, so how to begin and how to take the session forward. And we'll have a clarity, because what I believe is, let's spend this 2 hours or maybe another couple of hours in getting a clarity over the topic, instead of rushing into the multiple topics, multiple terms, terminologies. Let's have a clarity over small number of topics so that we can develop the what you call the fundamental concepts, and we can again begin. So yes, I'm familiar with and taught these concepts to the mechanical engineers. Okay, so I have got one response. Okay, good. So I hope, yes. Okay, good. So let us begin, and then that's good to see that people are familiar with the concepts. And this is what we are going to understand very soon. So the first thing where we are going to deal with is hypothesis testing. Basically is a concept to prove a statement, or say prove a research question which you have raised from sample data. Okay, so I'm getting some responses that familiar with the basic concepts only. So to deep dive into hypothesis testing, we need to have a very clear idea about first the normal distribution, which I mentioned, then the sampling. Why so? Because I'll talk about all these things in detail, why it is required. So when we start talking about hypothesis testing, what we are trying to do, so we are trying to get some inferences from a sample. And now the sample is what? A sample is a part of a population from where we are getting these data points. And our main objective is to give insight about the population characteristics. That means basically we have a large population, and because of shortage of time, or maybe the time limitation, cost limitation, so we cannot go to each and every customer or observer or the participant to understand what exactly is their feedback if I'm talking about some product. So the question remains, how to do that? So the process of getting the insight is getting a sample then. So there are multiple sampling methods available, And these are again bifurcated into two dimensions. One is called as probabilistic, another is non-probabilistic. So these sampling techniques will again give you the right idea to select the right sample. And then this is again another type of discussion which we need to have. Then once the sample is selected, so our motive is to understand the characteristics of the sample. So if the characteristics of the sample are same as the population or not. And while we are talking about a sample characteristic, it is very important to understand that these characteristics has to be measurable, because we are talking in terms of statistics where data matters. So we need to have a measurable data. So we need to measure these characteristics or attributes what we have gathered from this sample or the population in a larger picture. So let's begin. So I'm going to share my screen first so that we can have an understanding. So this is what we are going to talk about. And this is what we started with. So population versus sample. And the idea here is to give some insight or bring some insight, fetch some meaningful interpretation from the data what we've collected from a large population with the help of sampling. And then obviously we can generalize, we'll try to generalize. So it is more of approximation, it is more of predictions, what we are going to do. And this is what we are trying to learn. So when we talk about a population, there are some terminologies, and when we're talking about a sample, there are certain again different terminologies we have to utilize or use. So when we start talking about a population, we discuss parameters, and while we collect a sample from the population, so this sample has some characteristics, and these are called as the what you call the statistics, or say the what you call a parameter is now converted to a test statistics. And now using these statistics, we have to give an inference about the population. Now while we collect the data, the question again remains the same: how much sample size? What is the right or ideal sample? So again, there is a discussion which talks about the ideal sample size. But then again, because this topic is related to hypothesis testing, so we are not going to touch upon. But then this is also important part, that selecting the right sample and the right sample size. And all these things comes from another technique, this called as normal distribution. And this is why I asked about, there are some prerequisite which is a very important while we try to understand the hypothesis testing part. So suppose the population parameter is denoted by mu, a sign mu, and suppose the sample mean is denoted by x bar. So the idea here we are trying to do, if the sample is a right sample, then x bar will be approximately equal to mu. This is the ideal case. And this is what we are trying to test. So if there is a difference between x bar and a mu, what is the difference? At what level this is a difference? And this difference is again checked on the basis of some tolerance level. So these are the things we are going to discuss in the coming slides. So the first part was a population, and then from a population we have selected a sample. From a population there is a parameter, and from a sample there is a statistics, and we are trying to compare the parameter and the statistics if they are same or not, with the help of multiple techniques, or say the methods. So while we start talking about hypothesis testing, we need to have a statement, or say a claim or assertion about the sample. So that means the characteristics we are trying to check. So hypothesis is nothing but it is a claim or a statement about a unknown population parameter. Say, for example, in a pharmaceutical company, it claims that the efficacy of a medicine against a disease is 95%. That means 5% is the error level. And you can easily imagine if medicine is 95% efficient, it may cause a lot of trouble for the company, because you cannot say 5% is a very small number. 5% means it may kill many people if it is not working properly, right? Or if the disease is not getting cured. So in case of healthcare, 95% is a very less number. It has to go to 99.99%. So this confidence level will also change from, say, sector to sector, or depending on the requirements, right? Now, to test such claims, we have to collect data. And as I mentioned, collecting data is a time-consuming process. It has a cost associated. So we cannot go to each and every sample. So this is why we collect a small sample depending on our need. And there are formulas which can give you the idea of collecting the right sample size. So once we are having a right sample and the sample size, then we try to test the hypothesis or the claim which I have made about the population, right? And this process of managing, or say taking a decision about the population or about the characteristic of the population is called as hypothesis testing. The process involves, say, the collecting the sample, ideal sample size, then having said that there is sample, the right sample size is there, we have a statement, hypothesis, then we have to test the hypothesis with the help of a technique, and then there are some certain stages. So this is what we are going to understand in the today's session. So now the hypothesis or the statement is being made about the population. The question is, what all steps are involved? So before we go to the steps, we have to understand what are the types of hypotheses we can have for a population, right? So there are two types of hypothesis. One is called as directional, another is called as non-directional. So when we say there is a directional hypothesis or a non-directional hypothesis, that particularly means that suppose I'm not sure about the age of a person who is walking, say, on a road. So I'll say, I may have a statement that say that the age of the person is not equal to 35 years. So when I'm saying not equal to 35 years, that means the age can be more than 35 years and it can have less than 35 years. So because we can go in both directions, low and high, or say left or right, so this is why it is non-directional. But say when I'm looking at a mobile phone and I can say it is at least 5 years old, at least 6 years old, that means I'm giving a sign or a direction to my statement of more than or less than. So if your statement contains more than or less than, it becomes directional. If your statement contains a not equal to sign, then that becomes a non-directional, right? So in a hypothesis testing, there are certain steps which we have to follow. And these steps are, number one, firstly, we need to determine the null hypothesis and the alternate hypothesis. And we'll discuss all these things one by one in the upcoming slides. Then we have to select the level of significance, that is alpha. Then we have to select the right test. And this is why I mentioned that there are some prerequisite or requirements before we land up into this topic. So when I'm saying selecting a right test statistics, that means we need to have a good understanding of the z-test, t-test, ANOVA, chi-square, and so on. So these are the techniques which we apply in hypothesis testing to come to a conclusion. So step one was proposing a hypothesis, null and alternate, then selecting the alpha level, significance level, then the right test. And now we have to compare this test statistics with the benchmarked values. So these benchmarked values are coming from a table. So there are multiple tables. So for say Z, there is called a table called as normal table. For T, there is a T table, then there is F table, chi-square table. So there are some benchmarked values, which is already there in the literature, and we have to compare. We have to compare them. And after comparing, we come to a conclusion. So what we need to do, if we need to accept the hypothesis or we need to reject the hypothesis. And then further conclusion, or say the managerial insights. So if I'm accepting or rejecting, then what next? What is the next part, next process we are going to do? So as I mentioned, the first part was about null and alternate hypothesis. So null was the true, means assuming that the belief of a researcher is true about the population. So whatever we are having, and I'm trying to have a what you call statement or a claim about a population. So researcher has some certain beliefs. So that belief is made in a statement, and that is called as null hypothesis. And the remaining part, so say I'm trying to say that a mobile phone is more than 5 years old. So what is alternate? So it is, that means the reverse of that. So if I'm saying more than 5 years old, so that means less than 5 years is what my alternate hypothesis. So your belief about the sample, about the population, is your null hypothesis. And then the remaining part, so the contradiction part, is your alternate hypothesis, right? And the direction of the hypothesis is dependent on the sign you have made in the null hypothesis. So say for example, if in a null hypothesis you have a equal to sign, so you are claiming that the amount of water in the bottle is say 200 ml. So you can say that H naught is what? The mean amount of water present in the water bottle is 200 ml. So that it is having an equal to sign. And the remaining part, so if it is equal in the null, that means not equal in the alternate. So if there is a not equal to sign in the alternate hypothesis, that means it has two directions. One in the left, it can be less than 200, it can be more than 200. Similarly, if I am making a claim in the null hypothesis that the amount of water, the mean amount of water in the bottle is more than 200 ml, then the alternate is what? Less than 200 ml. So in this case, it is a one direction. So there are tests. There are different varieties of tests depending on the values you are having in the null and alternate hypothesis. One example can be, say, in case of equal to sign in a null hypothesis, the type of test will be two-tailed test. Why? Because it may have a less than sign and more than sign in the alternate hypothesis. Similarly, if it is more than equal to sign in the null hypothesis, then alternate hypothesis will have a less than sign. And this is why it will become a one-tailed test. Now, I have started talking about tails. So we will again describe the tails, and in which case we are going to have a one tail, in which case we are going to have a two tail, and so on. But then at this point of time, we are just trying to understand what is the meaning of a directional hypothesis and a non-directional hypothesis, right? So this is what I was trying to describe. So if it is a directional hypothesis, the terms such as positive, negative, more than are used to make a statement. If it is non-directional, that means there is a statement like no relationship, or there is a relationship, or something like that, right? So these are some what you call keywords which we need to apply before we form the null and alternate hypothesis. Now, because we have made a statement and now we have to go to a what you call a technique or a method. So we need to identify the characteristics, what we are trying to measure. If it is a age, if it is a gender, if it is a amount of water, it is amount of the volume of the gas, or so on. So we need to identify which parameter are we going to check. And to check this parameter, we need to have a clear understanding about a few values. And these few values are nothing but the descriptive measures. Descriptive measures means it includes the mean, mode, median, standard deviation, variation, and so on. Right. And at this point of time, I'm assuming that all the participants have a clear understanding about what exactly is mean, mode, median, variance, standard deviation, and standard errors are. So if there is any query related to these descriptive measures, surely we can discuss it right now, because in the upcoming slide, I'm going to utilize them to formulate a what you call a test statistics, which we are going to again utilize to come to a conclusion. So do let me know if there is any query related to the descriptive measures, what all they are. Okay, so there is a query about standard error. So you understand standard error, like say there is a population, and from that population we have so many data points, and suppose these data points are nothing but the age. So if we have the age of certain number of participants, then we know the standard deviation is nothing but it is the average deviation, average square deviation. The square root of the average square deviation is your variation, or say the standard deviation. So that means for that population we have a x bar, the mean of the population. Then we can have a difference of each of the sample point from this mean, that is xi minus x bar. If we square the values and then take the sum of all, that means it is going to give you the average amount of deviation of each of the points. Now the question is, if we keep on increasing the sample size towards infinity, what will happen? So if we increase the sample size towards infinity, the difference between the sample points and the mean, the observed mean, will become negligible, or it will tend towards zero. So standard error is nothing but it is sigma upon sigma is what standard deviation upon square root of n, and it gives you the average amount of deviation from the observed mean, right? Okay, in the chat box, I can see another thing that please share the statistical table PDF in this chat, like student T, F test, chi-square. Yeah, sure. Okay, and yeah, so I'll share the contents. I'll share all these contents, what I'm talking about, and I'll also give you some reading materials as well. I can always share the reading materials, which is required before you go deep dive into this topic of hypothesis testing, right? So now the question is, yeah. So the question is, we discussed about one thing called as hypothesis. Then we discussed about the type of hypothesis. It is directional, non-directional. Then we discussed about the type of hypothesis. This is null and alternate, right? So one is about the direction, another is about the description of the hypothesis. It is null and alternate. And then we started talking about the methods or the characteristics which are to be measured with the help of the methods. So these methods, one of the method is z-test and another is t-test and so on. And all these methods have certain assumptions. So we have to clearly understand in which case we can apply z-test, in which case we can apply t-test, in which case we have to apply, say, chi-square, ANOVA, and so on, right? Yes. So Narayanan has written something, null hypothesis H naught, alternate is H1. Yes, exactly. So these are the notations, H naught, H1. You can say write H naught or HA as well. So this depends upon how you're using it. So we have defined it. Now, there are certain assumptions we need to understand before we apply any test, right? So hypothesis testing is just a process. And before this process, there are multiple things we need to understand so that we come to a conclusion. So currently we are discussing about the steps involved. Steps involve the hypothesis testing, right? Now, so once we are clear with the idea that this is my hypothesis, it has some direction or not, and then we are clear with the idea which is the right test to apply, then the question is about what we can do. So are we going to accept the hypothesis or are we going to reject the hypothesis depending on the current data points? Now, before we go deep dive into the confidence interval part and the next part of this, acceptance or rejection of a hypothesis and the error part, I'm going to stop this here and I'll take you to the very brief discussion of the normal distribution and why it is required. I'll tell you in the upcoming next 5 or 10 minutes time, right? So I'll stop this here and I'll take you to the next part, which is very important before we go into the discussion of this hypothesis testing, and this is called as normal distribution, right? So this is what I was talking about. So one who is trying to develop the understanding about the hypothesis testing, he or she has to understand, or he needs to have a very clear-cut idea about what all is happening under this distribution called as normal distribution. So when we talk about normal distribution, we say it is a continuous variable and it has certain properties, right? And may I know from any one of you who is attending this meeting that why people call normal distribution as a normal? Why not some other name? What do we understand by a normal distribution, basically? Anyone? So the question remains why it is important to have a distribution like, say, normal distribution, and why it is called as a normal distribution. So you'll see that means while the research was going on, researchers or say the mathematicians or statisticians observed, yes, exactly, the nature of the curve. The nature of the curve was same all the time. That means for most of the experiment, the shape of the curve was coming to be same, right? And because it was coming same every time or similar every time, they said it is normal, because if it is different, then it is not normal. So the observation of the researchers or the mathematicians or the scientists was that they observed that this shape, this bell-shaped curve, is coming again and again. So you change the experiment for, say, any geography or any characteristics, but the shape remains the same. Because the shape remains the same, they said it as a normal. And if the shape is not in that bell shape, then they say it is a not normal distribution. And now we have to understand what all this normal distribution is doing. So normal distribution is giving you the idea about the graphical nature of the distribution of a random variable. So because we are collecting data from a large population and we are collecting a sample, So this sample has a distribution, and this distribution of the sample is called as sampling distribution. And now look at one example. So suppose we are going to have what you call a binomial distribution. It may include tossing a coin, or say on off or something like that. So experiment like which are having only two outcomes. So say, for example, I'm having a binomial distribution where the outcomes are only two, and we are trying to have the probabilities for doing the experiment thrice. So look at this. So while I'm having a values of x equal to 0, 1, 2, 3, the probabilities are given by 0 0.125, 0 0.375, 0 0.375, and so on. And we can plot this easily in the graph with the help of a histogram, and then you can see it has a shape. But here the number of experiment is only 3. If we increase this experiment from 3 to 4, 4 to 5, 5 to 6, look at this. What is happening? So the moment you keep increasing the number of time, or the number of occurrence, or say the number of times the experiment is happening, so the difference between, say, the width of these graph or the bars is decreasing. And if this experiment is done infinite number of times, then what do you think? What will be the probability of a single bar? So if this experiment is done infinite number of times, the probability of the single bar will be 0, isn't it? Because there are infinite number of bars, the probability of one bar will be 1 by infinity, and this is why 0. So this is why in case of a continuous distribution, the probability of a single bar is always 0. And we have to talk about a range of values. And this generates the idea of a continuous distribution. So in case of a discrete distribution, we talk about certain values. But then in case of a continuous distribution, we have to talk about a certain area, right? And this certain areas have some assumptions, you can say, or some properties which says that the total area under this curve is what? 1. The area is equally distributed, right? So look at this. So these characteristics is what? So the normal distribution has a property of this area is equally divided into 2 parts from the mean. The shape is bell-shaped in nature, right? And at this point, at the peak of this curve, the mean, mode, and medians are equal. So you can say at the peak of a normal distribution, you will get the values of mean equal to mode equal to median, right? And another property of a normal distribution is that it has a standard deviation equal to 1 and mean equal to 0. So we are converting a normal distribution to a standard normal distribution, where the standard normal distribution has a property that the sigma, the variance is equal to, the standard deviation is equal to 1 and the mean is equal to 0. And that is what is the basic of a z-test. So z-test is nothing but it is the standard normal variable, and standard normal variable is what? It is equal to x minus mu upon sigma. And this is observed from a normal distribution. So while someone is trying to apply a z-test, he or she need to understand what exactly is the basic of a z-test. So z-test is coming from a normal distribution, where normal distribution means a bell-shaped curve, symmetrical in nature, right? And at the peak of this curve, the values of mean, mode, median are equal, and the probabilities under this curve is equal to 1, and it is equally divided into 2 parts. So area in the right hand side from the mean is 0.5, area in the left hand side of the mean is 0.5. So these are the basic characteristics of a normal distribution, and this is the functional form of a normal distribution, which we don't need to recall. It is already there in the say Excel or CSPSS or the Minitab in the software. So we need not recall the formula, but yes, the gist of all the characteristics comes from this formula only. right? So whatever I'm talking about, this is coming from the formula only. So this is what I mentioned about. It is symmetrical in nature. At the peak, mean equal to mode equal to median. The area is divided into two equal parts. And look at this. So the mean can be anything. So mean can be negative, positive, or zero, but the nature of the curve remains the same, right? And look at this, another property. So depending on the values of sigma, so say in case of sigma equal to 1, it is a perfectly normal curve. If sigma is half, look at the blue line, it is more peaked, right? So depending on the value of sigma, we may what you call describe the nature of the curve. So if it is having a larger flat, what you call larger tails, less tails, or more tailed, so depending on the sigma values, so higher is the sigma value, right? Higher is the deviation, that means more flatter curve, and smaller is the value of sigma, more peakness is there in the curve. But then again, in all these cases, the property of a normal distribution remains the same. Area under the curve is 1, it is symmetrical in nature, and so on. So it is happening because of the change of the sigma values, right? And this is again another characteristic which I mentioned, that the area is equally divided into two parts. So nutshell, these are the properties, right? So one of the property is the curve is, this normal distribution curve is asymptomatic to the, or say the it is asymptomatic to what? The horizontal axis. That means what? It is going to touch the x-axis at infinity, right? Now, because now we have developed the understanding of what exactly is a normal distribution and how a z-score is generated. So z-score is what? Nothing but it is the z-score is x minus mu upon sigma. And now we have few more properties which says that if x1, x2, xn are, say, they are the independent normal variable, then their expected values is what? Nothing but the sum total of all the individual values. Similarly, the variance is equal to the individual sum of the individual variances, right? So say, for example, look at the example here. So it says that, say, for a automobile company, the summation of sales in a small segment, middle segment, and a high segment, right? So the total is what? The sum total of the small, middle, and the high, right? So we are saying that if the distribution in small, middle, and high are normally distributed, then the sum total will be also normally distributed, right? Now, another very important property of a normal distribution is, look at the area captured. So when I'm talking about a single sigma deviation, that means I'm considering the one sigma deviation means what? Mu plus sigma and mu minus sigma. So if in case of a normal distribution, we are trying to capture the area between a one sigma deviation, the area will be approximately 68.26%. Similarly, if I take 2 sigma deviation, the total area captured is 95.44%. And look at the third value. So if I'm considering the 3 sigma deviation, the total area captured is what? 99.72%, right? And this is what exactly you will see in the normal table as well, right? So once we'll try solving some examples or questions, you will see that these areas is mentioned in that particular normal table, right? Now, so this is what we have mentioned, and this is we are trying to understand with the help of a graphical nature. So look at this. So in all these cases, you will see the curve is what? Having some sigma value, some mu value, right? And the nature of the curve is same. And then obviously using these values, we can find the area between 39 to 41, 25 to 35, and so on. But how? So to find this area, we need to have a normal table, right? And Then to find the area from a normal table, we have to convert a value into the z-score, right? Say the standard normal variable. And z-score is what? Nothing but it is x minus mu upon sigma, right? So this is what I was talking about. So this z is nothing but x minus mu upon sigma. So we are given with the value of sigma and mu. I can easily calculate the z-score. And using the z-score, I can have the probability of that particular value, or say the range of values, right? Now look at, so to understand this whole concept, let us try to have one small example. So suppose that at a gas station, the daily demand for a regular gasoline is normally distributed. It is given, right? And a standard deviation of 100 gallons. The station manager had just opened the station for a business and notes that there is exactly 1100 gallons of regular gasoline. The next delivery is scheduled later today at the close of the business. The manager would like to know the probability that he will have enough regular gasoline to satisfy the day's demand. Or in other way around, if I'm trying to convert this statement into a miserable one, so I'm looking for a probability of a variable less than equal to 1100, right? So are we okay? So there is a chat in this meeting. What is meant by degree of freedom? So degree of freedom, so let's understand by it is the total number of independent variable. And when I'm saying independent variable, let's try to understand with help of example. So suppose I'm having two variables, x1 and x2. So the sum of x1 x2 is suppose 7. So x1 plus x2 equal to 7 is the value, and I'm looking for a degree of freedom. So in this case, a degree of freedom will be what? Equal to 1. Why? Because if I'm having a value of either x1 or x2, the value of the remaining variable can be obtained easily, right? So if there are two variables, degree of freedom will be 1, because if one value is known, another can be easily found out. Similarly, if suppose the sum of three variables is 7, so in this case, to have a unique value of all these three variables, I need to have at least two variables known. So for three variable case, degree of freedom is what? 2. And if I keep on increasing this sequence, you will see that for n number of variables, the total number of independent variables means what? The variables which can take any value on their own will be equal to n minus 1, right? Is this fine? Narayanan, I think this was asked by Narayanan. I hope I answered your question. And okay, good. So in this question, I hope the question is clear to all. Please let me know if the question is clear to all. Right? Okay. Great. So now the question is how to proceed. So we are looking for a probability of x less than 1100. And we are aware with the value of mean and the standard deviation. So as you can recall, z is equal to x minus mu upon sigma. So mu is given, sigma is also given, and I'm looking for a probability of x less than 100. So I have to convert this x into the standard normal variable. Okay, there is another question in this chat. How to predict the data? How to predict the data is sample data or population data? Okay, so in case of a hypothesis testing, you will see that we are always relying on a sample data, right? Because if the data is given for a population, then there is no need of hypothesis testing. So hypothesis testing is required because we are not able to have a data for the whole population, and we are trying to get inferences about the population from the sample only. And the question is about right sample size, and right inferences about the population, right? So in this question, we are looking to find the probability of x less than 1100. So how to do that? So to do that, we have to plot. So this plotting gives you the idea what exactly are we doing. So we have plotted the data, and because it was given that the data is normally distributed, so we have plotted the normal distribution data, normal data. And because mean was given to be 100, so this is my mean. So mean was 1000, mean was 1000, and 1100 is what in the right hand side of the mean. So we are looking for a value px less than 1100. That means we have to find the whole area, this whole shaded portion we have to find. And this can be found by the help of the standard normal variable, that is z, or c, say z. So z is what? X minus mu upon sigma. So now the question is, how do we do that? So one can easily do it manually as well. So if I'm writing x minus mu upon sigma, mu is what? 1000. So 1100 minus 1000, that is what? 100, divide by sigma, again 100, 100 by 100, 1. That means I'm looking for a value of z less than equal to, z less than 1. Now, there is another thing. Why we don't write z less than equal to, or say what will happen if I'm writing z less than equal to 1, or z is less than 1. So is there any difference? Is there any difference between probability of z less than 1 and z less than equal to 1? Anyone from the meeting who can tell me if there is any difference between writing probability of z less than 1 and z less than equal to 1? Okay, no difference. And why there is no difference? Why we don't have any difference between z less than 1 and less than equal to 1? Anybody? Because, yeah, because yes, you're right. And another argument can be, so as I mentioned, that in case of a continuous distribution, the values at a certain point is equal to what? 0. That means z equal to 1 contributes nothing. The area is what? 0. So this is why either you write z less than equal to 1 or less than 1, the values will remain the same, right? So we are looking for a value of z less than 1. So this can be done on, obviously, on Excel or SPSS or manually as well, or looking at the normal table as well. So if we go ahead and try to do that, so one can easily do that by writing in the Excel equal to normal distribution, and then it will return you the value. So while we are putting these descriptions of mu, sigma, and x bar, right? So it will return you value, and the value is coming to be 0.841. Now, the question, why it is 0.841 and what it signifies? What is the meaning of 0.841? So what do we understand by a value? So your software is giving you a value. The question is, what do we understand from this value? Or this value 0.841 is Means, do you all think that it is justified? 0.841, 84.1% out of 100%. Okay, meaning the interpretation of 84.1%. What is the interpretation of this 84.1% in our context, in our question? Okay, probability of what? So what do we understand by 84.1% or probability of 84.1 in our context? So if you remember, I'll again go back and I'll show you what was the question. So yeah, so it means less than 100. The probability of catering to the customer by end of day is 84%. Okay, perfectly fine. So we understood that if I'm looking to have the probability of X less than 1100, it is 84%. So that means approximately 16% in cases we are not able to satisfy the demand, right? So this is the interpretation of this this value, right? And as you all can recall, in the beginning I mentioned the area covered under 1 sigma deviation, 2 sigma deviation, 3 sigma deviation. So if you try to compare this, so how they all are in the same line. So if you recall, 1100 is what? 1100 can be written as what? 1000 plus 100. That is what? Mu plus 1 sigma, right? And we have read that in case of a normal distribution, the area is equally divided into two parts. That means in the left hand side from mean, the area is how much? 0.5, and the remaining 0.3413 gives you the 0.841, right? So means what? So you can easily identify that this rule, the rule of 68.26% in case of a 1 sigma deviation, it holds true in every case, right? And why? Because we have seen this by example, right? That the area captured by 1 sigma deviation in our case is what? 84%. So remaining part is what? 16%, which is coming in under the positive side of the sigma deviation, right? So this is what we have gathered from this part. And the manual part which I mentioned, this can be done through a normal table. So look at this. This is how it will appear. The standard normal table will look like this, where the values of Z for a single decimal are given in the vertical direction. And for the second decimal place, you have to go for the horizontal rows. So in our case, say, means in our case, it was 1 only, but say one who is trying to capture the value of Z at 1.56. So for the 1.5 will go vertical direction. In a vertical direction, 1.5 is here. And from the second decimal place, we have to scroll to the horizontal direction. And you can see that for the value of 1.56, the probability is coming to be 0.4406. And please mind that while we are using a Z table, what if someone is asking you to find the what you call the probability of Z less than 1.56 only? Tell me what will happen if I'm asking not from 0, I'm asking probability of Z less than 1.56. So what is the difference between probability of 0 to 1.56 and probability of Z less than 1.56? Anyone in the meeting, please? Yes. So if someone is looking for a value of Z less than 1.56, that means they have to include the area in the left hand side as well. And the area in the left hand side is what? 0.5. So 0.5 plus 0.4406 will be the area for Z less than 1.56. But if you're looking for a value of 0 to 1.56, the value will be 0.4406, which is excluding the value in the left hand side. Right now, so are we good till now? Is there any query? Is there any query related to the description of normal distribution, the z-score, the area, the interpretation of the area, or anything? If there is any query, please let me know. Z is not clear. Okay. So z-score, this z-score is obtained with the help of a formula. Yes, the table is only for the right side of 0. Yes. So this z-score is nothing but it is a formula which is given by x minus mu upon sigma, right? So we need to have these values. So x bar, if x bar is given, mu is given, and your sigma is given, then you can calculate a z-score. So suppose your x bar, or say z table is already given to you. Yes, these values, so the table and what I'm talking about, so these table are already given to you in, say, in the literature, it is already there existing. And otherwise you can always utilize the softwares, say in case of Excel or SPSS or Minitab, you will find these values automatically by help of a syntax, right? Or say you can write a small formula which I mentioned earlier in case of Excel. So you just put the values and then you'll have the values already there in the software. So in case of manual calculation, you have to find the z-score by writing x minus mu upon sigma, and where this x bar, mu, and sigma are already given. So if you have a value of z equal to, say, anything, say suppose you are having a value 1.95. So what will be the z-score? What will be the z-score in case of z equal to 1.95? So participants, can you please give me the value of z-score for 1.95? What will be the value of z-score or the probability for z equal to 1.95? So for 1.95, what we need to do, we have to scroll vertically down till 1.9, and for the remaining 0.05, we have to move in the horizontal direction. So I'll move, you can see my cursor is going on, and then it will go till this. So this value 0.4744 is the value, or say the probability corresponding to the z value of 1.95. Yes, exactly. So I hope I made the point clear how to calculate it. Okay, good. So let's move ahead. And this is what we discussed. So similarly, if you all are clear with the idea of the normal distribution, so can I expect an answer for this question as well? So read the question carefully, and I am looking for an answer. I'm looking for an answer of this question. So read this question carefully, and if you have your notebook or you have a pen paper, you can easily draw the diagram as well, and try to find the value. This is a very small question where uh, we need to apply the normal distribution, and everything is mentioned here in the slide, and you just have to apply that, and then you have to determine the answer of this question given in the slide. So those who are from operations research background, operations management background, or mechanical engineering, they must be knowing. uh, I hope the question, the word stock out is clear to all. So because there are some terminologies like stock out, replenishment, and lead time, so I believe you all are aware, familiar with these terms. So let me know if you all are comfortable. If not, surely we can discuss this here only in this meeting. Okay, so I have got one answer from Mr. Prasad. Please mind that we are looking for a probability. The question is asking about what is the probability that the demand during the lead time will exceed 20 gallons. Exceeds. Okay, so I'm taking you to the next part, the solution part. So look at this. So this is what we are trying to do. So I mentioned that Z is equal to, or say Z or Z is equal to X minus mu upon sigma. And we got the value of Z equal to 0.83. So this is a normal simple calculation, 20 minus 15 by 6. And we are looking for what? Exceeds, right? That means we are looking for a probability value of X more than 20. That means we are looking to find the value of probability of Z more than 0.83. Now, before we deep dive into this answer, we have to firstly understand which area we are targeting, right? So that means we have to look for the area. Now, the area which we are looking for is this one, right? And in the normal table, the question is, in the normal table, you can have a value for the z-score only for 0 to that particular point, right? So the normal table gives you the area under the values, area under the range of 0. That means from mean 0 to that point. So we are interested in this area, but in the normal table, the area will be given for 0 to 0.83. So the question is how to do that? So we know that there are two ways. So we know that the total area under the curve is what? 1. And we have to find a value from the normal table for Z equal to 0.83. So look at this. I'll just go back and look at this. For 0.8 and 3. So for 0.83, look at the cursor. So the value is what? 0.2967. This is the value. So either you do this way, subtract 1 minus 0.5 plus this. Why 0.5? Because 0.5 is the area in the left hand side, plus 0 to 0.83 is what? 2967. So 1 minus this total is what? This area. Or other way around, you could have done in other way. The area in the right hand side is how much? The area in the right hand side is what? 0.5. So 0.5 minus 0.2967. So there are two ways. Either you do this way or do the other way around. Subtract this value 0.2967 from 0.5. You'll have the same value, 0.2033, right? Okay, so there are different chances. I can see 0.7033, 1 minus 8.33. So that is not possible. There is a one answer like 1 minus 8.33, so value will be negative. So here the idea is to calculate the probability, not the z-score, right? So I hope I made my point clear that what are we looking for? We are looking for our probability values, and probability values can be calculated only if the z-score is there, and z-score can be calculated if the x bar, mu, and sigma. X bar is what? The sample mean. Mu is what? The population mean. Sigma is what? The standard deviation, right? Okay, so Felix, could you please let me know what exactly you didn't understand? Is it the whole question or only this part?
Only this part, sir.
Only this part. Okay. So firstly, what we have found that the value corresponding to what? Value corresponding to x more than 20 will give me z more than equal to 0.83. Now, we have got a value of z equal to 0.83. For z equal to 0.83, the probability. So to find the probability corresponding to a z-score, I have to go to the normal table. And the normal table, which I showed you earlier, look at this. The normal table says that at z equal to 0.83, look at this, the value is how much? 0.2967. And we were looking for this area. This area falls in the right hand side. The area in the right hand side is how much? It is 0.5. 0.5 minus the area from 0 to 0.83 is how much? So 0.5 minus 0.2967. So with that, you can have a value, right? Okay, so Deepthi has a question. But if normal distribution having a value negative, so how it responds? Normal distribution. See, you have negative values, no? Means in this case, suppose the value is negative 0.83. Suppose you are getting something like negative 0.83. So basically, we know that the area is what? Symmetrical. So either are we talking about value less than 0. minus 0.83 or plus 0.83. It remains the same. Why? Because the area is symmetrical in nature, right? Okay. So why I am talking about these things? Because this is minimum required before we land up into the second part. Okay, so Sunil has a question: probability of z more than so Sunil, is this your question, or are you trying to explain me something? Because you have written probability of z more than 0.83 is 1 minus this. because what you have written is, yes, we know that probability of say P plus Q is equal to 1, because table is only right hand side of 0. Yes. So Sunil, to answer this question, we can have another table. So normal table is given for only for the right hand side, and also for, say, including the left hand side. So we can have two tables. One table is only for the right hand side value, assuming that you know that the left hand side is 0.5, and there is another table of normal which adds the value on the left hand side. 0.5 is added, right? So I was talking about why we are trying to understand this, because before we go to the hypothesis testing, we have to have a very good understanding about which area are we talking about, right? And this will give you the understanding of the left-tailed or the right-tailed as well, which I mentioned in the hypothesis testing steps. So if something is falling in the left hand side, it is called as left tailed, or if it is falling in the right hand side, it is called as right tailed, and if it is both, then it is called as two tail test. So one is a case of one tail test. So one tail means what? Either left or right. When it is two tailed, that means both the tails are included. So it may, the chances of occurrence is in the both directions, right? So this is what is the case, right? Now, because we have a now understanding about the normal table and how to do that, now I'll take you to the next point, right? So this is one part. So I'll stop sharing this, and I'll take you to the second part. This is very important to understand. So this part is the extension of the normal distribution. So as I mentioned, hypothesis testing can be understood well if we have good understanding of normal distribution, then z-square, then the z-score, then the third part is what? The sampling distribution. I'm not talking about sampling. So sampling is a theoretical topic, or we can have a separate discussion over this. So now we are talking about sampling distribution. That means here we are going to talk about the sampling errors, or they say the standard error and so on, and how the formula is generated, right? So in case of sampling distribution, obviously the rules of probabilities and the laws of expected values will be assumed to be true here, and I'm assuming that participants here are well aware or familiar with the rules of probabilities and the laws of expected value and the variances, right? So what we are going to do, so we are going to derive the formula for the standard error. So why I'm saying that the standard error is equal to sigma upon root n, right? This is the idea here. So we are going to understand why the formula for the standard error is sigma upon root n. So to understand that, let's have a very small example of rolling a die one or twice, or maybe then n number of times. So we know that in case of rolling a die once, the probability of each number is what? 1 by 6. And by the formula of mean expected value, the mean will be equal to 3.5, the variance equal to 2.92, and the standard deviation is coming to be 1.71. Now, if we repeat the same experiment twice, if I'm tossing a die twice, and then recalculate the mean and the standard deviation and the variance, look at this. So if I'm tossing a die twice, you all know that the sample can be 1, 1, 1, 2 till 6, 6. And these are the mean values. Look at this. The mean of 1, 1 is what? 1. Because 1 plus 1, 2 divided by 2 is 1. 1 plus 2, 3. 3 by 2 is 1.5, and so on. So these are the sample. These are their means. And we know that in tossing a die twice, there are 36 possible outcomes, right? So we have to calculate the mean, combined mean. So look at this. So we are trying to find the mean, and mean is coming to be 3.5, which is same as what we have calculated in case of single toss of a die. That means either you are tossing once or twice, the mean value is not changing. But here is the part which I'm trying to bring. So if I'm calculating the variance with the formula,
Can you please share your slides? So it's not visible right now. The new one.
The new one. Okay.
Yeah.
I'm going to share it again. I hope now it is visible.
Yeah. Thanks. Okay. Yeah, it's
Okay.
not visible.
Okay. I'm so sorry, Miss. I don't know, Miss.
No, it's okay.
I tried sharing, but then I missed.
Yeah.
So
Okay, it's okay.
I hope we all are on the same page. So let me know if you all are on the same page. So when we are tossing a die once, the mean is coming to be 3.5 and standard deviation is coming to be 1.71. When I'm tossing a die twice, the sample values are these. The mean are calculated here. And if I'm using the formula, I'm getting the mean value equal to be 3.5, which is same as the earlier case. But the standard deviation is coming to be 1.21. So in the earlier case, it was coming to be, look at this. In the earlier case, it was 2.92. And here it is coming to be 1.46, which is exactly half. Right. So if I continue the same thing again and again, you will see that the mean remains the same. And the standard deviation, or say the variance, is slashed or divided by the number of times I'm doing the experiment. And this gives you the formula, the generalized formula. So look at this. In the first case, you were having a flat distribution. If you keep increasing the number of times you are doing the experiment, look at the graph. The nature of the graph becomes bell-shaped. So this is for a single toss. This is for a twice. That means 2 times. If we keep increasing the number of times the experiment, you will see that the graph will take the shape of a normal distribution. And for this normal distribution, the mean value remains the same, but the variance changes to sigma square upon 2. So for 2, it is 2. For 3, it is 3. 4, it is 4. So for n, it is sigma square upon n. So if variance is sigma square upon n, so standard deviation is how much? It is sigma upon root n. And that is what is the formula of a standard error. And this is why I mentioned that if you keep increasing the number of trials, the error will be 0, because n tending towards infinity, the error will be 0, right? But the mean will remain the same.
Excuse me, sir.
Yes.
Actually, sir, once please revise from the first slide in short.
First slide, this one.
Yes, sir.
Okay.
Okay, this is okay. Mean and standard deviation.
Right. So
And
this is the case where we have tossed the die only once.
okay.
Right.
Fine.
Now, if I'm tossing a die twice, so we will have 36 outcomes starting
Yes.
from 1, 1, 1, 2, 2, 6,
Okay.
6.
Okay. Yes.
And for all these samples, the mean will be what?
Okay.
Mean,
Okay. Some of these two.
yeah.
Yes. This.
And then we again have to apply the formula of the mean and variance. So while I'm applying the formula of mean and variance, you can see that the mean value remains same. It is coming to be 3.5. But
Okay.
the variance is coming to be 1.46. But in the earlier case, it was 2.92.
Okay.
Right. So if we continue the same thing again and again, what will happen is you will see the generalized formula. This is what I'm trying to mention. Or this generalized formula says that in case of n number of times you are doing the experiment, the mean will not change, but the variance will change by divided by
sigma
n.
square by n. Okay.
Yes.
Thank you, sir.
And this gives you the idea of standard error. Right. So far we have discussed about normal distribution, where the z-score value was how much? It was x minus mu, or say x bar minus mu upon sigma. Now in case of hypothesis testing, as I mentioned, because we are taking a sample and it can be n number of times, the sample can be selected n number of times, right? So this is why in case of hypothesis testing, we talk about a sampling distribution. And in that particular case, we have to use standard error in place of a sigma. So the difference between standard normal variable and the value utilized in a hypothesis testing, the only difference is what? The sigma value. In case of normal distribution, it is only sigma. In case of hypothesis testing, it becomes sigma upon root n. Why? Because from a larger population, we can have n number of sample, and these n number of sample have a distribution. This is called as sampling distribution, right?
Yes, sir.
Okay. So that is what I was trying to give you, trying to describe about the need of understanding of sampling distribution and the normal distribution before we'll end up into the hypothesis testing. Now, there are a few more things. So I mentioned about the assumptions of each and every test, right? So suppose the value of sigma is known to you, right? The value of standard deviation is known to you. So if the value of sigma is known and the population size is very large, so in that case, we utilize z-score, or say the z value, or the standard normal variable. But in the case, if it is unknown, say sigma is unknown to you, and the sample size is less than, say, 40 or 30. So for different literature, also for the existing literature, you'll see that we define the small sample by saying n less than 30. So if it is a small sample, n less than 30, and your sigma is unknown, your sigma is unknown means what? Population standard deviation is unknown. In that case, we have to apply t-test. So there are varieties of tests depending on different assumptions, right? And that is what we are going to apply in the hypothesis testing. So once we understood which test has to be applied, then we can obviously go for the application of hypothesis testing, and then we can define what exactly is the inference from the population, inference from the sample about the population. So before we go into that part, we need to understand few more terminologies, and this is called as estimator and estimate. So what is estimator? So say you are taking n number of samples, and from n number of samples, you are trying to find the mean of the population. So if you are trying to find the mean of a population with the help of the mean of the sample, this mean of the sample is called as estimator, and the value of the mean is called as estimate. So I'm just going to repeat it again. So estimator is a variable which estimates the value of a parameter, and parameter belongs to population, and estimate is the value of the estimator, right? Estimate is the value of a parameter, and estimator is a variable which is trying to estimate the parameter which belongs to a population, right? So x bar, in terms of notation, x bar is called as estimator, and value of x bar, so x bar can be, say, 3.5 or 4.5. So value of x bar is called as estimate, right? So these are the definitions. And now we have to understand the difference. The difference it brings in the terms of z-score when we are doing a sampling distribution, right? So what is the difference between, say, when you are doing a sampling once or twice or thrice and so on? So what is the impact of these sampling on the values of the z-score, right? So that is what we are going to understand now in the upcoming slide. So I'll skip this part because this is, again, we have understood this part. So I'll skip this, and these are the notations which we have already discussed. So look at this example. So suppose the mu, right? This mu is what? The population mean. The population mean is 16 inches. And sigma, the population standard deviation is 0.8. Then we have to determine the following. First part, what is the expected value and the standard deviation of the sample mean derived from a sample of 2 pizzas, and then in a case of 6 pizzas. So if you look at the values of expected value of mean x bar, in both the cases it is 16. And I would like to know why it is 16. Why in case of sampling 2 pizzas or in case of sampling of a 4 pizza, the expected mean remains the same? Anyone from the meeting, please? Why the mean value in case of sampling of 2 pizzas, in sampling of case 4 pizzas is equal to 16? Why it is not changing?
Population mean.
No, this is because we just read that in case of sampling, the mean values do not change. If you recall, in case of a die, in case of tossing of dice, the mean was not changing. So it comes from that particular, you can say, the definition or the theorem, which says that when we do a sampling, the mean values do not change, but the standard error changes and it becomes sigma upon root n, right? So yeah, so this is why the mean values remain the same, but look at the standard errors. In case of 2 pizza, standard error is 0.57. In case of 4 pizza, the standard error is 0.40. And you can easily understand by these values, if you keep on increasing the number of pizzas, say 4 to 8 to 16, the standard error will keep on decreasing and it will become 0. It will become 0 when the n is tending towards infinity, right? So now we have understood that the mean remains the same in case of sampling distribution, and there is an impact on the standard error. So we can move forward, and then you see that there is something. So
excuse me, sir.
Yes, please.
It means when n tends to infinity, it will suppose sample we are taking that is infinite. Then in that case, standard deviation will become 0.
Standard error becomes
sorry. Standard error will become 0, and the sample mean and population mean will become the same. That is always same.
Exactly. And then this is again in a simple language, layman's language. Suppose I'm saying that my population is my whole say student body at my organization. So if you are looking for a feedback, then either you can go to 2 student, 4 student, and 6 student, right? So in that case, feedback. And if you're talking to each and every student in the organization, in that case, the feedback. So in which case the feedback is right? So the ideal feedback is what? If you're talking to each and every one. So if we are talking to each and every one, means what? N is what? N is what? Infinity. That means N is capturing the whole data. So if N is capturing the whole data, that means the sample mean and the population mean becomes equal, the ideal case.
Okay.
Right? And this is why standard error becomes 0 in that case.
Is
right?
this central limit theorem?
Yeah, no, central limit theorem is different. It says that, say, if a population is distributed normally, right? As per central CLT, central limit theorem, it says that, say, if a population is normally distributed and you are taking sample out of the population, then each sample is also normally distributed.
Okay.
So that is different. And this says that in case of n is tending towards infinity, the sample mean and the population means become equal, and it is the ideal case.
Okay.
Right? Now going ahead, we have now discussed about the standard error and everything. So look at this. So if you all recall, we have just discussed, in case of a normal distribution, the formula was x minus mu upon sigma. Look at this. But in case of a sampling distribution, the formula becomes sigma upon root n. So this is the basic difference between a sampling distribution and a normal distribution, right? So why it is divided by sigma upon root n? We have a clear idea about that. Okay.
Yes, sir.
Similarly, suppose mu is 16. The population mean is 16, and the population standard deviation is 0.8. We have to determine something. So it is asking, what is the probability that a randomly selected pizza is less than 15.5 inches? Mind you, we have selected a pizza. That means the trial is only once. So in that case, you can easily understand that we are looking for probability of x less than 15.5. So we have calculated the value corresponding to 15.5. It is coming to be minus 0.63, right? And then we are looking for a probability of z less than 0.63. Now the question, why probability of z less than minus 0.63 is coming to be 26.43, and what is the area? So anybody who can tell me what is the area we are looking for? Or are we clear with the idea which area we are targeting?
Yes, area is less than minus 0.67.
Minus 0.63 and minus 0.63. Yeah, and minus 0.63 lies in what?
Left side.
Left hand side.
Left side of the 0, and then we can reverse it because it is symmetrical.
Exactly. Because it is symmetrical in nature, so we can reverse it.
Yes.
Right. And you all know now how to find the what you call the area corresponding to 0.63, right? I believe you all are now having a clear idea how to find the z-score corresponding to 0.63 and which area will be. So mind you, while we are looking for a normal table, we have to subtract 0.5 minus the area between 0 to 0.63, right? So the area will be 0.5 minus the area between 0 to 0.63, right?
Can we say this way also, sir? Probability of z less than minus 0.63 is equals to probability of z greater than 0.63.
Yes, exactly. Why not? Because the area is symmetrical.
And that is equivalent to
0.5
minus 0.
Yes, area between 0 to 0.63. Yes, exactly. True. So I hope you all are on the same page and you are not feeling content heavy. If this is the case, we can surely have a small break here and then we can again continue. If not, then I can continue for the next part, because we have covered so many terminologies, and there are so many terms going to come in the next half an hour or 1 hour time. So let me know if you all are comfortable with this content, what I have covered so far, or if there is any query, please let me know.
Sir, if the case of z less than just instead of minus, if it is 0.63, do we need to do 1 minus?
No, we don't need to do anything in that case. If it is only z less than 0.63, that means it is already capturing the area from 0 to 0.63. Right? So in that case, we don't need to do 1 minus something or 0.5 minus.
Can you come again, sir?
I'm saying, suppose it is probability of Z less than 0.63. That means it is by default capturing the area from 0 to 0.63. Right? So in that case, we don't have to do 0.5 minus whatever is the value of 0.63.
In case, suppose it is greater than 0.63 means, then in that case, we have to add the 0.5.
Yes. Subtract. If it is more than 0.63, that means we have to subtract 0.5 minus 0.63.
It comes in the right side, the small
part. Yes. It will come in the right hand side.
Thank you, sir.
Right?
Sir, excuse me, sir. I think there are two normal distribution table. In one table that shows from left side to right side. Like for example, Z less than 0.63. It means in that table from left to negative side and with 0 to 0.63 all entire.
Yes.
Okay. In one table, one normal distribution table.
Yes.
And this table shows only 0 to 0.63. So this is a little bit confusion. In some cases.
So I personally prefer to use the table which is only for the right hand side. Why? Because we know by default that the area is symmetrical in nature and the area in the left hand side and right hand side is 0.5 each. So instead of using the table where 0.5 is included, I prefer or I suggest everyone to use the table which I showed earlier, in which the area is captured only from 0 to 0. Whatever the value is, right? Because in any case we know the area in the left hand side is how much? 0.5. Area in the right hand side is how much? 0.5.
Okay.
So suppose in this case, in our case, it is asking probability of Z less than minus 0.63. That means you are looking for a left hand side.
Yes.
You are standing in the left hand side and you are looking for a value lesser than 0.63, right? So if you are looking for a value lesser than minus 0.63, that means what? We have to subtract from 0.5, isn't it? Because the tail is towards left.
So my question is actually, sir, if it is Z less than 0.63, it shows that 0.5 plus 0 to 0.63.
No. It depends on the table you're looking at. So this is why I'm saying again and again, we have to be very specific about which table we are looking for. In this case, why we cannot go below 0? Suppose the value is asking about Z less than 0.63. Suppose this is the case. I'm removing the minus sign. Suppose I'm asking probability of Z less than 0.63, right? So why I cannot take a value less than 0? The question is that because the length are always in a positive value. It's absolute value. Length is always positive. So we cannot take a value which is less than 0. So this is why we cannot add 0.5 in that case. Right? Because it is talking about a length.
I understand this way, sir. Actually, I just message you. The probability of Z less than 0.63 means 0.5 plus 0.2357. But according to this table, 0.5 is not there, only 0.2357.
Only, yes. The correct answer is only 0.2357.
Okay.
And why we are not including 0.5? Because length cannot be negative. So this is why we are not considering the value below 0.
Okay.
Right? I hope this is fine.
Yes, sir.
Okay, good. So, so far we understood. Yes. So far we understood that how to calculate the Z square. And in this case, we were looking for a single case where a single pizza is selected. Now, if I extend this same question and if I ask you, what will happen if I'm selecting 2 pizzas? So now look at the change. So earlier we were taking only sigma. But the moment I am increasing the number of cases from 1 to 2, I have to use the formula sigma upon root n. Right? And I believe you all can follow why it is sigma upon root n. So, yes, why it is sigma upon root n? I believe everybody can follow this.
Yes, sir. Yes, sir.
Yes. So the moment I am taking for 2 pizza case, the probability becomes 18.94%. Earlier it was 26.43%. So can we have an inference? What will happen if I keep on increasing the number of pizzas? Yes, please. Anybody can just give me the inference. What is the inference? Yes.
It will reduce to 0.
It will, yes, it will keep on decreasing.
Yes.
Why it will keep on decreasing? Because as I mentioned, because the moment you keep on increasing the sample size, it will ideally take what? The sigma value equal to mu, the x bar equal to mu. Right? The two means become equal. The population mean, or say the population mean or the sample mean becomes what? Equal. Right? Or in this case, means you can see the trend. So for 1, it is 26.43, for 2, it is 18.94, and then if you increase the number of cases, it will keep on reducing, right? So, having said that, all things are covered about the sampling distribution, about normal distribution, their properties, the theorem, the important theorem, which we are going to utilize again and again, this is called a CLT, which I mentioned. Right? For any population X with expected value mu and a standard deviation sigma, the sampling distribution of X is approximately normal if the sample size is sufficiently large. This is one, right? And as I mentioned, for small sample case, we are considering 30 as a benchmark, right? So if n is less than 30, we say a small sample. If it is n is more than 30, we say it is a sufficiently large sample, right? So if the sample size is large, we have to use a formula of z score equal to given by this x bar minus mu upon sigma upon root n. But the moment n is less than 30 and sigma is unknown, we have to use another test. This is called a t-test, right? So we have to be very careful what exactly is given in the question and which test are we applying. And this has to be what you call, this has to be recalled every time whenever we are doing a question or we are trying to prove something. We have to be very careful if all the assumptions holds true or not, right?
Excuse me, sir. When n is less than 30, then we have to use t-test.
And
what is the reason behind it?
Reason, yeah. So t distribution is applied for a small case where the number of samples are countable, right? And if number of samples are countable, then we can talk about degree of freedom. Okay. So depending on different degree of freedom, the shape of the normal distribution changes.
Okay.
And this is why we have to talk about degree of freedom as well as the normal distribution, because for a different degree of freedom, we have different normal curves.
Okay.
And if n is more than 30, we have to talk about a single curve, which is a normal distribution curve, right? In case of 30 degrees of freedom, yes. So if say the sample size is 30, the degree of freedom will be 29. So degree of freedom is nothing but n minus 1, right? So, and that is all means we cannot cover hypothesis testing. I must tell you here this, that we cannot cover hypothesis testing in say 4 hours, 5 hours or 6 hours. It can take number of days. It can take number of days and hours to understand the whole concept, right?
Sure.
This is more like a brief. I'm trying to give you the brief idea about what all we do in hypothesis testing. But to have a clarity, we need to have n number of sessions to describe each and every feature, right? Because it is divided into several type of tests. The tests are also parametric, non-parametric tests. And then in case of Z test, T test, T is also divided into multiple parts. So there is a, what you call, a chain of tests which you have to test. And for each and every test, there are certain assumptions. And for each and every assumption, there are certain formulas which you have to test, which can be done through a software. And this is why software becomes handy, because it can give you the idea of if the assumptions are holding, assumptions hold true or not. So this is only a brief idea about hypothesis testing, what I'm sharing right now. But then this can take maybe a month's time to understand each and every part. Right? So this is only a single part which I'm describing, and I'm trying to cover the basics, the fundamental part, which is very, very important before we land up into hypothesis testing. Right? So please pardon me if I'm not able to cover each and everything, because I don't believe that means I am capable of covering each and every part within say a span of 4 hours or 5 hours. Means in fact, you learn these concepts in years sometime. You teach n number of times, you learn, then you do mistakes, and then you can revise, and then you can again learn. So it's a continuous learning process. And again, this continuous learning process is again a normal distribution curve where you make errors, right? So this is a learning process.
I think we can give a short break, right? Like 15 minutes or something. It's already long hours. Yeah.
I do understand. Yeah, and this is why I was asking the participants if they are feeling comfortable with the content, because it's a really content heavy session.
Right, so, right. They have to be very careful in listening, like every single thing. Yeah, I think maybe it's better to give 12 minutes break, and then you may start at 5 or something, like after 12 minutes or something. Or what do you think?
Whatever you say, Professor, Miss, I'm perfectly fine.
No. I think it's up to you. Like when you want to give. So we have basically in our calendar break from 4:30 to 5 maybe.
Okay.
Right? So
okay. So we can then begin at 5, and then we can try to cover at least the next part of hypothesis testing, so that at least we can have a few examples from hypothesis testing before we conclude.
Yeah.
So
I think you have almost 10 minutes. Like you have 10 minutes left. Like if you want to give a break at 4:30, so it's up to you. Like you can reduce the gap, or if you feel that you need to cover more, so it's up to you. Yeah.
Okay.
And the participants.
Okay. So it's better to have a feedback from the participants that if they are comfortable with the content I have covered so far. If they have any queries, we can discuss the query in the next 5-7 minutes, and then we can again resume at 5, and then we'll try to cover the next part of this session. Yeah, for sure. I'll share all these content and PPTs and whatever resources I have. So, and then you all can connect me. Means I am available. So you can see my LinkedIn profile. Like I can be the part of the conversation or discussion every point of time. Right. So, Professor Ali, Miss, please suggest. Yeah.
I think it's up to you, because participants said that they're happy, and if you are happy, then you can just continue as you wish, like up to the end of the session. So it's up to you.
Okay. Yeah. So what we'll do means we'll have a very short break, and then we'll again resume the session, right? So instead of starting from maybe 5, we can start at 4:45 then, and then we can begin for the last part, right?
Yeah, that would be good. Like, yeah. So